Hi, this is Bernard Brault. This is part 3 of a series I'm doing on light, photons, radio waves, electromagnetic waves, but from a quantum mechanic approach. And in the first video, I went through the math, and what I explained is if you have a photon with a known energy, fixed energy level, that photon will be in a energy eigenstate, and the known amount of energy depends on frequency, and the way such a state evolves is that it stays the same, so the energy is conserved over time, except that its amplitude is multiplied by a phasor. And these phasors can cancel each other out, or they can amplify each other or cancel each other out depending on how they're lining up when they arrive from multiple different paths. So I was at the stage of sort of opening up a camera lens or a camera aperture, and then what we're looking at here is we're looking at all these light rays, and of course this is a fairly wide opening, so what would happen is that the shortest path here would arrive with a certain phasor, and most likely the paths very close to this one would contribute to increasing the probability of arriving here. But definitely as you move farther and further out, then you're gonna have other paths that are gonna start canceling things out. So what if you want all of these paths to contribute, to all the phasors to be all lined up? What can you do? Well, you could play a little trick, and the trick's following: is you slow down the light in the direct path so that the time it takes for the direct path to reach the screen at the far end, or the sensor or the film, is the same as the time it would take to actually reach if it went directly. So not directly, went through that long path here on the aperture, the widest aperture. Same thing at the bottom. So what you have here is, if you chose that piece of glass, because light slows down in glass, and you slow it down to a degree where this beam and the top beam and the bottom beam arrive, all three of them at the same time, then you know what, their arrows will add up. So what about the other ones? Well, this one here needs to be slowed down compared to that one, but not as much as the direct one. So that one would have like a piece of glass that would be a little bit smaller, because it doesn't need to have as much slowing down. And then same thing with these. And next thing you find out is that what you're building there is a lens. And interestingly enough is that you can calculate the shape, the geometric shape and the width of the lens at every single point with very high precision, only with Excel, for example, and then you'd be able to shape this lens exactly so that it behaves the way you want. You'd have to know how much the lens slows down the light, and this you have to remember that the slowing down depends on the frequency. So this light would focus, this lens would focus red light, may not be so good, and that's what they call chromatic aberration, where different colors don't focus on the same place. I'm not going to go down this road, but that's what happens. If on the other end you're trying to focus light rays that come from far away, then the lens may have a different shape, and you could again do something similar here. Let's move on to something a bit different. If you remember in high school, let's talk about a geometric shape called a parabola. And if you remember what a parabola is made, the way to make a parabola is you need to have a line, a straight line, and a point. So here in blue is a point, here's a straight line, and each point on the parabola is equal distance to the point, which we'll call the focal point, and to the line, and I'll show you a couple of examples, right? So the orange point right there is exactly the same distance from this line, perpendicular of course, and to the focal point. Same thing with green, so this green line here, green dot line, is the same as here, and the red line is, so it's constructed that way, right? So and each one of these points, as long as they're equal distance between the focal point and the line, then you're forming a parabola. And a parabola is a It's a quadratic, it's a second degree. Simplest one is y equals x squared or something like that. But I don't want to get into the y equal x squared part of it. Just remember what I just described here. So imagine now that you've built this parabola, and then you have light rays coming from far away, like a distant star, and these light rays will all come parallel because the point is so far away that all the lines coming in from that star are all parallel, and then they're going to hit the mirror at different locations. So for example, it could hit the parabolic mirror right here, and what would happen is that the time it would take to actually reach the focal point here is equal for all the parallel rays. And that's pretty obvious because the time it takes to go from here to there plus the time from here to the focal point is the same time as going from there to that other line right there. So all of the parallel rays that would come between this line to that line are all equal, and therefore that means that all of the possible paths of going from here to the point when after it hits the parabolic mirror, they're all arriving with equal timing. And if they all arrive with equal timing, that means that the probability of hitting this focal point is extremely high. And this is why, you know, parabolic mirror work very, very well for astronomy, for example. You can build pretty big telescopes with that. All right, so let's move to a different shape. This time I'm going to talk about an ellipse. If you remember how to build an ellipse, you could do this by you know, hitting two nails on the board and having a string, and you move the string around. The string that's a bit longer than the distance between these two, and then you move the string around. And as you move the string around, you're basically building the ellipse, because what happens is that an ellipse has the following property, that, you know, the length of, you know, the red dot here and the green one is the same. So no matter where you go from point A, you hit the ellipse somewhere, and you go to the second focal point, that's always going to be equal distance. So and because it's equal distance, again, we can use it, you know, in order to focus light. And how we would do this is something like that. So all of the dotted lines there, green, red, they all arrive. It all takes exactly the same amount of timing. So instead of wanting to focus parallel lights, you're trying to focus something that's a bit closer to you, and you want to focus all the light through to another focal point. Then you build an elliptic mirror just like that, and then what's going to happen is that all of these are going to have, all these paths, potential paths, will have all equal time, and therefore the phasors are all going to be lined up, and you're going to have a huge peak at this particular point right there in terms of probability of light hitting there. You got to be careful to protect the direct path right here, because that might interfere actually. So it's all equal distance as long as you're only taking the reflection points. Speaking of ellipse, I don't want to give up ellipse so quickly. Let's look at the microwave, let's say licensed 6 gig microwave radio or 2 gig microwave radios. These are like fairly tall antennas, and they're like 200 feet up in the air, and you got your transmitter 50 kilometers apart or so, and the direct path will, let's say, have this kind of phaser, and there'll be another path out there, right, that's going to go up and then back down, and that other path somehow will come in at 180 degrees and start canceling out. And that other path, let's take a look at it with an ellipse if you want. So when you have an ellipse, let's say for example that a path that would be like 50 meters apart there would arrive 180 degree difference. That means that anything that reflects, or any point that actually uses a path that hits this ellipse right there, would be canceling out the main signal. And that path there is called the first Fresnel zone. We call that the first Fresnel zone. It is an ellipse around the two, and the two transmitters and receivers are focal points on the ellipse. And you build this, and there are multiple zones, because if you actually expand, go a little bit further out. Oh, before I do that, within the Fresnel zone, as long as you don't approach this cancellation in place, as long as you stay within 70% or so, what's going to happen is that every one of these paths there, even though this is like maybe like 60-70 meters high, every one of those points contribute to improving the signal strength on the other side, because these arrows are all pointing more or less in the same direction. They start pointing in the opposite direction when you hit the first Fresnel zone, which is the edge of this ellipse. Now, there are more than one Fresnel point, and that's what I want to show you. So zone 2 right there, see the fastest path, or the primary path, may have a phasor that's like this. The zone 1 would be a canceling one, right? Completely opposite. But once you reach zone 2, all of a sudden zone 2 is far enough so that the phasor did an additional 180 degree and is lined up with the fastest path, so it contributes. So what you have here is you have zone 1 that is destructive, zone 2 constructive, zone 3 destructive, zone 4 constructive, right? And when you're designing a radio path, you try to be careful not to have obstacle at 70% of your first Fresnel zone. You try definitely not to have reflection, like a body of water that would be sitting on zone 1. And if on the other end you have zone 2 that with some reflection, well, that reflection will help, and microwave path designers are very, very much aware of this. But going back to the zone, so if you remember the even zones, zone 0 if you want the direct path, zone 2, zone 4, and there are more, all of the direct zone, or the zone even zones, all contribute. So if we had a way to cancel out zone 1 and then zone 3 and somehow block it out, then we would be able to amplify the signal. And you could do this, and actually it would look like something like this, right? So what you see there is in black is where light can go through, and the white bands are Fresnel zones. This is zone number 1, and it blocks the light. And by blocking the light where it would arrive at 180 degree and cancel out the signal, if you could do this, then you actually can build yourself some kind of a focusing lens. And these are called Fresnel zone plates. They're used in X-ray microscope, and there's been some discussion of building something like this in space for a space telescope. It'd be very simple to build. You'd have two structures. You have a structure that would be like this. It could be 100-meter big, so it would be a 100-meter lens. It would be completely flat. It might spin just to make sure it stays flat, and it would be made out of these sort of Fresnel circle. And further out there, you'd have another vessel that would be capturing the light from this, and it would be a magnificent telescope. And some people are talking about building something like this. Now, speaking of Fresnel zone, let's go back to our laser pointer, right? If you're actually shining a laser pointer at a fairly long distance, you go out there in the dark and you find a road, and you take your laser pointer and you send somebody out there 1 kilometer away, right? So he's pretty far away. He's probably going to need to have a scope or something like that to be able to see this light there. But the Fresnel zone actually is going to be right in the middle here, about a foot. It's going to be about 30 centimeters. So what's kind of interesting is we always tend to think that light travels in a straight line. But in fact, it uses pretty much, I'd say, 70% of that 30 centimeter radius right there in order to reach out there. If you were to just block the very middle of it, you'd still see that laser dot. And that's kind of amazing, isn't it? Because we've been brought up to think that light travels in straight path. In fact, it doesn't. It takes multiple paths, and it's the accumulation probability of all these paths that actually make a difference. So that's about it for now. Oh, one last thing, one more application. I have 30 seconds. All right, I'll do it in 30 seconds. Radars on airplane, fighter aircrafts. They have a radar in the front. They try to track other airplanes, so they try to actually aim the radar at the other plane. And the way they do this is with a phase array. So they have all these little transmitters right there, and the transmitters. Oh, I may not have enough time.